Thank you. So this is, first of all, thanks to the organizers for the kind invitation, especially Subhro. So this is what I plan to do. I'll first talk some general information about quantum phases and their classification, and then go on to a comparative study of quantum spin liquids versus conventional states of matter to show how unique properties quantum spin liquids have. And then I'll describe experimental results on two families that we have been working on. So the research theme in my group is to discover new materials and study phases of electronic matter in them. And these are some of the common states of matter that we have been looking at in the past. And so the existing paradigm in which phases and transformation between phases was understood was the Landau paradigm, where spontaneously broken symmetry is used to differentiate phases from each other. For example, so if you have a paramagnet which is cooled down and goes into the ferromagnetic state, it loses, the spins lose the rotational symmetry that they have in the paramagnetic state, so they've broken a symmetry. So these phases can be characterized by a local order parameter and understood within a mean field like models. But in the last several decades, we have a new paradigm, the topological paradigm. And within this paradigm, there are two kinds of classes of topological phases. One is where the topology arises from Berry phases in the bands, and these are like the integer quantum Hall, topological insulators, and the Dirac and Weil semimetals. Also topological magnons, which have recently been introduced. So all of these can be understood within a non-interacting theory. But there are other phases, topological phases, which actually have topological order. And fractional quantum Hall and quantum spin liquids are examples of these. And these states have ground state degeneracy. So I mean, you put them on a manifold like a torus or something, you'll get a definite number for the degeneracy. These states are characterized by long-range entanglement, and the excitations are fractional. So as an experimentalist, the most easily accessible out of these three is the fractional excitations, and that is what I will try to show to you in two classes of materials. So to first just contrast spin liquids versus conventional magnets, let's put spins on a square lattice and let them interact via a nearest neighbor Heisenberg interaction, antiferromagnet. So then when I cool the temperature below this scale J, they order into a nail state. And so it has, this state has broken the spin rotational symmetry, as I said, and the ground state is approximately a product state. We can define an order parameter, which is the staggered magnetization in this case, and it follows a behavior which can be understood within mean field. Now, if I create an excitation in this ground state, I have a delta S equals to 1 excitation. But this cannot be fractionalized. If I try to move the grain boundaries apart, as I try to here by flipping spins, we can see that the energy cost to pull the defects apart grows as the length, the separation between these grain boundaries, and therefore it is energetically not feasible. So therefore, this excitation that I have created cannot be broken into parts. The consequence for a neutron measurement is that you will have a sharp absorption. So the neutron comes in with a certain energy and loses some energy to the sample, and that will be a sharp excitation at a fixed energy, which is given by this J. And the dispersion will be spin wave-like, so sharply dispersing bands. In contrast, if instead of a product state, I build up the ground state from singlets, which are actually entangled, Then I have several situations. Some of this we have seen in Subir's talk. So if the singlets form this static pattern, then it's called a valence bond solid, because even though the spin rotational symmetry is preserved, it breaks lattice symmetries. So this is not a liquid. A liquid would be formed if I allow these valence bonds to resonate, either short range or long range. And then a superposition of all such coverings of the lattice will be the ground state. And this will, you will see that such a state does not break any symmetry of the Hamiltonian, and you can define no local order parameters for this. And this state will be characterized by entanglement between spins, all the spins at the same time. So this is what I would call a spin liquid. So if I create an excitation in a spin liquid, you can see that I create a single, I flip a single spin and create this excitation. And now, because of this RVB nature of the ground state, these spins can move apart independently of each other and act like two independent particles. So the excitation, delta S equals to 1 excitation that I have created, has broken up into two parts. And these quasi-particles carry spin, but no charge. And there are other kinds of excitations in a spin liquid as well, like Subir mentioned. If you have vacancies, then these would be holons, and they move around with a charge but no spin. So the consequence of this fractionalization for a neutron measurement would be that the sharp dispersive continuum, sharp dispersive spin wave-like excitations are replaced with replaced with the spin-on continuum, because so the neutron loses some energy, and now it has to be distributed between these two particles, the two spin-ons, because they are created in pairs, and there is no unique way of doing this, and therefore there is a continuum of excitations. So I show this a real data for a quasi 1D magnet, calcium, potassium, copper fluoride, and this actually, there is weak interchain coupling, and therefore this material orders at 5K or something. So if you have, if you do measurements at high temperatures, you see this spin-on continuum, but as you lower the temperature, you begin to see spin waves out of the ordered state finally. So this is an example of fractionalization in a quantum spin liquid, an experimental example. So for 1D, you will have this particular shape, but for higher dimensions, these shapes will be more complicated. And but the bottom line will be that you will have a continuum of diffuse excitations which are not have no structure. I don't know if I should talk about this in front of theorists, but the point is that if you take a snapshot of a RVB and draw some hypothetical line which cuts a certain number of bonds, this number would be either even or odd depending on the size of the lattice you've chosen. And now the point is that in any local rearrangement of these RVBs, this number does not change modulo 2. So if it's even to start with, it stays even and so on. So this is like a topological invariant if you want. Yeah, so this parity can only be violated if you do some non-local rearrangements of these RVBs. You take the spins which you have broken and move them all the way across to the edges of the sample and then create a singlet out of them. So then to summarize, the quantum spin liquids have no order parameters that you can, no local order parameters, no broken symmetries. There is massive entanglement and the excitations are fractionalized. Topological order and emergent gauge theories, which is above my pay grade. So as an experimentalist, how do I search for quantum spin liquids? What are the experimental signatures that I will find? So the first thing is that I have an interacting collection of spins which don't order, and therefore the absence of long-range order can be found in thermodynamic measurements like the susceptibility and heat capacity. The spins will be continuously fluctuating even to the lowest temperatures, or at least temperatures much lower than the interaction scale. And these can be measured via NMR and MUSR like measurements. The fractionalization, for example, spin-ons in this RVB-like picture that I showed, can be measured through inelastic neutron scattering experiments. And whether these spin-ons are mobile or gapped can be measured by thermal conductivity, heat capacity, and so on. So, I mean, we have an interacting system which doesn't order. So the point is that the quantum fluctuations are so strong that they suppress any ordering tendency that the system would have. So if I want to build a quantum spin liquid, I go to small spin, low dimensionality or low coordination, and geometrical frustration, mostly antiferromagnetically coupled spins on triangular motifs is the recipe that experimentalists use to look for spin liquids. I need some water. Sorry. So there are several experimental examples of frustrated lattices built out of these triangular motifs, both 2D and 3D. And the surprising thing is that whatever lattice that theorists can dream up of, nature has already thought about it. So all these lattices have actual realizations. And so as an experimentalist, I wanted to just tell you how the experimentalists go about constructing lattices. So, for example, I have worked a lot on the Kitaev-like materials. So, I will construct a Kitaev lattice out of rock salt. So, this is the sodium chloride structure. Of course, I want a magnetic atom on it, so MnO. If I look down the 111, I see that the manganese is already sitting on triangular lattices. So, I can view this as a triangular lattice of manganese and oxygens and manganese and so on, stacked along the 111. This, however, cannot be called a 2D triangular lattice because there is strong coupling in the third dimension, in the between the planes right now. So if I can somehow increase the separation between the triangular layers, I could make this quasi two-dimensional. So what one does is, if I replace half the manganese with the lithium, I will replace every second manganese layer with a non-magnetic layer and end up with the manganese, oxygen, lithium, oxygen, manganese. And now this is a system where the manganese triangular lattices, triangular planes are actually well separated. And indeed, LiMNO2 exists, and people have done a lot of studies on this for frustrated magnetism and so on. If I further remove 1/3 of the manganese and replace it by some non-magnetic ion, I end up with the honeycomb Kitaev lattice. Okay. And if I remove a different fraction of this manganese, I could get the Kagome. So all of this can come from the rock salt itself. Okay, so let me go to the first material that I want to talk about. So large crystals can be grown by optical furnace if anybody is interested. So the space group is this with a large c-axis, but you will see that the c-axis has a lot of atoms in it. The structure is built up of these bilayers which are stacked along the c-axis as shown. And if I look down the c-axis, I see bilayer Kagome planes. So each Kagome plane is made up of two kinds of triangles. The up triangle have an interaction which is called J triangle 1, up triangle 1, and then there are down triangle 1. 1 is the top layer and 2 is the bottom layer. So the point is that the sizes of these triangles are different, and triangles of one kind are surrounded by triangles of the other kind and so on. And in the layer below, the situation is reversed. The big triangle is connected to a smaller triangle, and the smaller triangle is connected to a bigger triangle. Now, we have done inelastic neutron scattering on a polarized state of this material and extracted the exchange parameters. So I'll tell you already why this material is frustrated. So the interactions are, the strongest interactions are actually ferromagnetic. The down triangle in the bottom layer and the up triangle in the top layer are both ferromagnetic and strong. And the down triangles in the up layer and the bottom triangles in the bottom layer are antiferromagnetic and weaker. So the point is, if I just look at one of the layers, as I cool the temperature down, the spin half chromium 5 plus will first couple into a effective spin 3 halves, which is then sitting on a larger triangular lattice. So if left to itself, if I just had this top layer, I would get spin 3 halves on a triangular lattice, which would give me 120-degree order. But what happens is that the two Kagome layers are coupled by this J inter, which is a ferro. So the frustration mechanism can be understood from just taking one triangle on top of the other. So the top triangle is ferromagnetic and wants to align the spins in the same direction, whereas the bottom triangle is antiferro and wants to have a 120-degree order. But the coupling between the top and the bottom triangle is ferromagnetic. So that is the mechanism of the frustration in this system. Yeah, so yesterday somebody talked about lucky accidents. So discovery of this material was also a lucky accident. I was working a long time ago now on these bilayer triangular lattices, barium and strontium, manganese and so on, also with chromium. And the point there was that this vertical bond was the strongest, and therefore this became a valence bond solid with a large gap and so on. And in field, this gap could be closed and you could see a BEC-like phase transitions and so on. So this was for the bilayer triangular lattices that I studied long time ago. And I was trying to make the calcium analog of that. And you see, if I rewrite this formula, I actually get something very close to this. And this would be a triangular lattice. But if I remove now half of the calcium, then the chromium valence has to change. Out of the 7 chromiums which were earlier magnetic, 1 becomes non-magnetic. And therefore, the triangular lattice changes to a Kagome. So that is the origin of the discovery of this material. So this is a busy slide, and it is a collection of almost all data we have on this material. But let me walk you through it. So this is the magnetic susceptibility, and it is featureless. A fitting gives spin half for the chromiums and an exchange coupling strength of about 2.5 Kelvin. μSR measurements, also heat capacity measurements, which I'll show later, show that there is no ordering or spin glass at all down to the lowest temperatures measured. And you can see this is 19 millikelvin, 2 orders of magnitude smaller than the Y scale. And the relaxation rates become temperature independent below this 300 millik or so, just like you would expect for a spin liquid. Inelastic neutron scattering on powders here and on single crystals here with the momentum transfer within the Kagome planes is shown. There are 2 energy bands between these energy ranges and these energy ranges. And you can see that this scattering is completely dispersionless. It's very diffuse, and it's like the continuums of spin-ons that one would expect for fractionalized excitations in a spin liquid. I will talk about the structure within these bands later. So preliminary thermal conductivity measurements by Matsuda's group have actually shown that it extrapolates to some finite value at low temperature. So this may be a gapless state. So this is again the neutron structure factor in these two bands. So you see that there are two bands, one at low energies and one at higher energies. So this is a cut through one of the lower bands, the bottom of the lower band, and higher up, but again in the lower band. And this is in the higher band. And so Johannes Reuter's group has done extensive calculations using a model of spin-ons, and they are able to reproduce these structure factors very nicely. Yes, yes. And the heat capacity measurements again down to 20 millikelvin. At low temperature shows a linear temperature dependence in almost one order of 1 decade in temperature. But at the lowest temperatures, if I plot it on the log scale, I see that the heat capacity falls lower than the linear dependence. So what they have done is, so the initial model was of free fermions. And then looking at the heat capacity data, they've added some pairing, weak pairing, and they've come up with a spin-on band structure. So they say that the linear heat capacity at intermediate temperatures is coming from this Dirac-like band, and this small gap is what is causing this dip in the heat capacity, which may or may not be exponential. We don't have enough data yet. So whether it is the gap is S wave or F wave, we don't know. The calculation is done using an F wave gap. Yes, on the Kagome. Dude, that is an effective model that you can take. So if you look at the Kagome, it has spin halves on the Kagome, but I am saying that these large triangles are ferromagnetic in nature, and therefore, as you cool the temperature, there will be some temperature at which it will act as an effective spin 3 halves. Spin half. I think I don't. I mean, Johannes does. I think it's a spin half on the bilayer Kagome, but I'm not sure. I can get back on that. Very small. So less than a MeV. So thermal conductivity is not sensitive to disorder. Heat capacity is.
Density of states is very low energy. How do I understand where does that?
I see. Okay, right.
Kappa would be very positive for itself.
Yes. Yes, that is what I said. So both. So as I will mention here, both semi-classical work by you and Nick Shannon's group have used that model where they say that effective spin 3 halves on triangular lattice also gives the same magnetic structure factor. So, but I mean, aren't there examples of magnets where a quantum model as well as a classical model gives the right structure factor, but people talk about quantum to classical correspondence, right? Yeah. So this Nick Shannon uses a spin half on an effective honeycomb, I think, right?
There was this other calculation
Right. So my point is that there is large frustration, even though the effective spins could be 3/2. There is strong frustration, and therefore we do not see any classical order down to 20 milli-K when the exchange scale is of order 10. So therefore, there must be some quantum fluctuations present in the system. But I mean, we can discuss later. Okay, how much time do I have? Okay. Okay, so the next family of materials that we have studied is the Kitaev materials. This should be a summation sign. So this is a model on the honeycomb lattice, which is a bipartite lattice and should not be frustrated if the exchange was Heisenberg-like. But these exchanges are Ising-like with the following issue, that the Ising axis on the three bonds coming out of a vertex are in three orthogonal directions, and therefore this is the reason for the frustration in the Kitaev model. Maybe I should also skip this. This is just the pattern construction of what Kitaev did to exactly solve this model. But this is where fractionalization of the spins into two kinds of Majoranas comes about. I'll just show you the thermal fractionalization as a function of temperature. So at in the ground state, we have a uniform flux order, and the C Majoranas are moving around the honeycomb lattice and will give Dirac-like dispersion. At finite temperatures, there is a gap to these flux excitations, and therefore the flux begins to get disordered. And finally, at some high energy scale, the Majoranas then all couple to become these paramagnetic spins at high temperature. So there are two temperature scales at which different things are happening. So the first materials which actually had the right ingredients to show this Kitaev material were these iridates, and this is actually an old story now. And various 3D models, 3D versions of these were also discovered later. And ruthenium chloride, which has actually become the front runner now because neutron scattering measurements on this are easier to do. So both materials unfortunately order at low temperatures, but there is, at least for the sodium material, there is a large window in which one can see that the ordering is actually suppressed from where it should have if it was just a mean field magnet. And direct evidence of this bond directional exchange was obtained from diffuse Rix experiments done by B.J. Kim's group. So here they've measured spin component resolved spin-spin correlations along different directions. So when they look at SXX, which is the SX coupling to each other, they see intensity only along one bond. If they look at SY, they see intensity along another bond, which is perpendicular to this one, and SZZ is again. So a calculation was done on what the SXX, for example, should look like if the model had Heisenberg versus Kitaev. So in the Heisenberg limit, you would have completely isotropic intensity distribution, which is not seen here. In the spin liquid, of course, everything is diffuse, but as soon as you add a small amount of Heisenberg, you get structures which we see here. So this broken spin rotational symmetry, even above the Néel temperature, with the three spin components exhibiting short-range correlations along distinct crystallographic directions, was actually a strong evidence of Kitaev interactions, the real space and spin space coupling to each other. So Motome has done quantum Monte Carlo simulations to extract finite temperature properties, thermodynamic properties of this model. And this is one of the predictions that they had, which is that the heat capacity will have two sort of bumps. The entropy will be released in two steps, and this will approximately be at half, the plateau will be at half log 2. So we did heat capacity measurements on the sodium iridate and approximately see two-step release of entropy with half R log 2 in the middle of the plateau as predicted. So this is one maybe thermodynamic signature of fractionalization. A new material, copper iridate, which does not order at all down to the lowest temperatures, was also synthesized by us. And you can see that even though it has an exchange which is similar to the sodium iridate, it does not actually order down to the lowest temperatures. This is AC Chi, which is also featureless, and therefore it rules out any spin glass also. MuSR confirms that this is a dynamic state down to the lowest temperatures, again 250 milli-K. So Raman scattering done by Ajay Sood's group looked at phonons, and these phonons were riding on some background. And if I take the integrated intensity and plot it as a function of temperature, I see the data in the inset here. So if this background was just coming from phonons, it would have reduced in this fashion as bosonic background would. But you see that at a scale of about 100 Kelvin, this takes off and goes up and starts increasing as the temperature is lowered. So if we subtract this bosonic background, I am left with something which can be fit with a fermionic distribution temperature dependence. So this we feel is another evidence of some fermionic quasi-particles being present in this material below this energy scale, which from the susceptibility measurements is the Kitaev scale. What also happens is that at this temperature scale, the phonons start misbehaving. So this is the frequency at which the phonons occur, and this is the bandwidth of the full width at half maximum of the phonons. And you can see that almost all modes, and specifically this one, behave anomalously below this temperature scale. And Subhro and his group has done some calculations on Majorana phonon coupling to explain these very nicely. This is the Fermi function. Sorry? We just see that the temperature dependence is fermionic-like. Instead of bosonic, which would go down in temperature, we see some magnetic excitation which is going up in temperature. So Raman, which is an inelastic measurement, usually measures phonons, which should only give a signal which goes down with temperature. So we are suggesting that this is coming from some fermionic excitations of these examples. Okay, to summarize, topology and entanglement are new principles to classify quantum matter, and quantum spin liquids are examples of such highly entangled states. And I showed you two examples. The experiments on calcium are consistent with the QSL with spin-on excitations, and copper iridate is a new Kitaev QSL candidate with no order down to 3 orders of magnitude compared to the theta, and Raman scattering shows evidence that fermionic excitations may be possible, Majoranas or something. Thank you.
Thanks, Yogesh. We have time for a couple of questions.
So, quick question about nomenclature. When you call, what do you call Kitaev paramagnet? Is that the Kitaev spin liquid, the gapless spin liquid?
So, yes.
Interesting. I'm not really from this field, but in terms of the probes that are available, one is neutron scattering, other is Raman. Are there other probes like measurements of velocities or with anisotropic strain, which have some smoking gun evidence? Yeah, maybe. Of this of the spin liquid sort of response from the system. I mean, Raman is accessible, but at lower temperatures it becomes trickier to do Raman.
Right. So because these are all strong insulators, experiments like tunneling, etc., which can be done on these fractional quantum Hall systems and so on to see that the charges are actually reduced, all of this cannot be done here. So we are confined to experiments which can be done on insulators. So one experiment that can maybe try to look at spin-on Fermi surface effects is that you sandwich, let's say, a quantum spin liquid between two ferromagnets, and as you vary the thickness of the quantum spin liquid, you can have an RKKY-like coupling between the ferromagnetic layers, and with an insulating sandwich, this would only occur if you have a gapless spin-on Fermi surface. So that is one experiment that has been proposed to look at spin-on Fermi surface. But I don't, that is the problem. So the entanglement and the topological order is very difficult to experimentally access, whereas maybe it is easier, the fractionalized excitations are easier to measure.
Any other questions? If not, let's thank Yogesh again.